So, hello everyone. How are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we're literally gonna talk about the thing that I have written over here. Basically, we'll come over that later on, but before that, let me just tell you about something. Actually, it's been quite a long day. It's been a long day since I just recorded myself standing here and teaching you on board because actually some of my latest videos were on tablets, right? Actually, I was suffering from fever and I was like sick, right? Because the temperature outside in my area is like reaching up to 42 degrees of Celsius, 43 even. So it's literally very hot in here, and I cannot record any video without AC. So, and you know what, the condition of electricity in my area is also very sick. So I just have to suffer with that. So yeah, actually it's all right, and I hope everything is fine with you, right? Because the temperature is quite rising up to a lot of peaks, I think. Yeah, for sure. Okay, so now let's just not talk about those things, but let's come in our zone, in mathematical zone. Okay, so here I have written something: infinite product representation of infinite sum of evens Riemann Zeta function. Like, let me just explain it to you a little bit here. So what does that mean? That, let's say this is an infinite product, right? And the representation of this infinite product in terms of this infinite sum. So this is the sum, and the argument of that sum, or the argument of that sum, what is Riemann zeta? Wait a second. Riemann zeta of 2n. If I'm talking about if n is going from 1, or obviously from 1, because n is 0 is it's Riemann hypothesis, because when n is 0, well, we will not talk about that in this video. So basically we have to talk about this thing. Like, can you imagine the infinite sum of Riemann zeta function that is being represented to an infinite product? Wow. So like, that sounds cool. Obviously that's really sounds very cool, right? Well, it's not something like that, and we have to do something we have to talk about the argument of this product, and it's not yet. Actually, we have another argument over there, so well, we'll talk about that. Okay, basically, again, whatever I'm just gonna use in this video to prove this down, or maybe prove this down in this video. Everything I have covered in my older videos, and obviously whatever things that I'm going to use in this video, I'll paste the link of those things in the description box, so you don't really need to worry about that. And literally I'm just going to use 3 things. I'm sorry, actually one thing that I haven't covered yet, and I'll cover it soon, right? Wait a second. And the thing is that the infinite product of cosine function. Okay, let's now talk about that. You know what? It was quite recent that I have uploaded an infinite product of cosine function. So the thing that I have proved is cosine of z equals the product as n goes from 1 to infinity of n squared pi squared minus 4 z squared over n squared pi squared minus z squared. So we have proven this thing, right? But another it's not this standard representation as an infinite product of cosine function. We have a standardized, like, standard product. Now let's say infinite product. So what's the standard infinite product that represents the cosine function? So it is cosine of z equals the product as n goes from 1 to infinity of it's 1 minus 4z squared over 2n minus 1 squared pi squared. And yeah, I'm really sorry because I haven't uploaded the video or the proof of that yet, but yeah, I literally, because I'm just gonna use this, although I can just use this down and end this video up because I have proved this thing, but I just want to show you some magics in mathematics. That's why I'm just gonna use this one as well. So for this one, just wait for few hours or maybe few days. I'm damn sure, and I'm just giving you a guarantee that I'm just gonna bring a video on this, and then we would and again when I'll upload the proof of this video, so I'll just paste the link of this video in this video, like the description box of this in this video, right? So don't worry about that. So basically, yeah, right. Now let's talk about the representation. Wow, that sounds cool. And you know what? We ain't gonna just prove the representation. Actually, we are just going to play around with that as well. So basically, yeah, this is how we should begin. So when we were talking about, like, I have uploaded a video proof the infinite sum representation of cotangent function. The first prerequisite and the foremost prerequisite for this video, actually, because we are gonna begin our proof from here itself, and I have uploaded the proof of the thing that I'm just gonna write it down here. So, and again, I'm just gonna paste the link of that as well. So basically, pi z cotangent pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n and z to the 2n. The infinite product that the infinite sum that has Riemann zeta function of even arguments, and that with some things extra, and that too equals pi z cotangent of pi z. Wow, that sounds good. We have proved this, right? Yeah, actually I have proved that. I have not my tablet with me right here, or maybe I'll paste the link of that video, don't worry. So yeah, from here we are just going to begin our journey. And you know what? Cotangent of pi z can also be written as the ratios of cosine of pi z over sine of pi z. And now you can just think of something that I'm just going to represent these two functions as infinite products. So basically, the left hand side of this equation becomes, well, I can write that as pi z over sine pi z and times cosine of pi z. You know what? This pi z over sine pi z reminds me of something. If you are a real mathematics student, so you know about this. The Euler's reflection. We have talked about a lot of times about this actually in our previous videos. Formula. So that says gamma of z times gamma of 1 minus z equals pi over sine pi z. So if you are going to multiply this z both sides, so that's gonna give us gamma of 1 plus z times gamma of 1 minus z equals pi z over sine pi z. Basically, how did I write the z times gamma of z as gamma of 1 plus z, it's an identity, right? Because you can write this as z factorial. So this can be written as z times z minus 1 factorial, right? And z minus 1 factorial is gamma of z. We have talked about that as well. Everything, like, except this one. Except this one, we have everything. We have proved that all the things in our previous videos. Wow, that sounds good, right? And now let's just talk about the infinite product of this thing, right? We have just extracted this thing from here, and then we would be just representing this this thing here, like infinite products here, and that's it. It's easy. It's literally easy. Okay, so the first things first, that we have cosine of z equals this infinite product. So there we can just replace z with pi z. So that's gonna give us. Let's talk about the first infinite product that I have evaluated personally. It's not a standard infinite product of cosine function. I have evaluated that, and I have never seen anywhere about this. I have ever seen the cosine function as an infinite product, the one that's called as a standard form, right? And this is my personal one, I would say. Maybe some mathematicians have evolved this, or maybe calculated that as well. So we have to just replace everywhere z with pi z. So that's gonna give us n squared pi squared minus 4 pi squared z squared over it's n squared pi squared minus pi squared z squared. And now you can just see that we can just plug out pi squared common from the numerator as well as from the denominator. Wow, that sounds good, isn't that? So that's gonna give us I think I just made some mistakes that I have written in my notebook actually. Yeah, this one is good. So cosine of pi z equals, so this pi squared cancels out with this one because we can just factor that out. So we are left with the product as n goes from 1 to infinity of n squared minus 4z squared over n squared minus z squared. So this is our cosine of pi z. And now what about, like we are having cosine of pi z, but again we have to talk about pi z over sine pi z because it was also there, and we have to look for the infinite product for that as well in order to get a perfect infinite product. And now we have Euler infinite product of sine function. And again we have proven this actually a lot of times. You know what, this sounds crazy, and the thing is we have sine z equals z times the product as n goes from 1 to infinity of 1 minus z squared over n squared pi squared. So this is your Euler infinite product of sine function. And I think I have proved this in three different ways. And the most easiest one was from the double angle formula of sine function. I must recommend you to watch all those videos. Like, yo, those were great. Now, in order to get sine pi z over, actually we were looking for pi z over sine pi z, right? But now you would ask, Aman, you are looking for sine z. right? Yeah, like we are having sine z as an infinite product, then how would we able to reach from here to there? So just be patient, guys. I'll make sure you would not get any kind of confusion. You just have to replace z with pi z here. So that's gonna give us sine pi z, and this z is gonna be pi z as well. And the product as n goes from 1 to infinity of, it's 1 minus pi squared z squared, and this was n squared pi squared. Pi cancels out, right? And let's divide both sides with pi z. So that's going to give us sine pi z over pi z equals the product as n goes from 1 to infinity. So that can be written as n squared minus z squared over n squared. And now just taking the reciprocal of both the sides. Since it's the product, so we can just take the reciprocal of that easily. And if it were like it was sum, so I think it's not easy to take the reciprocal of the argument of that sum. But for product, we can just take that. So pi z over sine pi z comes out to be the product as n goes from 1 to infinity, the reciprocal of this argument, n squared over n squared minus z squared. So here is your thing. Oh my goodness, like we are having cosine of pi z as this infinite product, and we are having pi z over sine pi z as well as this infinite product. And now we're just gonna multiply these two infinite products in order to get this equal to the right hand side of the like this sum of the Riemann zeta of arguments in even arguments, right? I hope you are getting me. Let me just write that down. So we are having cosine of pi z as the product as n goes from 1 to infinity of n squared minus 4z squared over n squared minus z squared, and pi z over sine pi z, the product n squared over n squared minus z squared, right? Okay, that sounds good. So here it comes. So yeah, basically we were having pi z over, wait a second, sine pi z cosine of pi z equals 1 minus 2 the sum as n goes from 1 to infinity of Riemann zeta of 2n and z to the 2n. Okay, now let's just represent like both of these like terms as like they're separate infinite products. So the first one is having the product as n goes from 1 to infinity of n squared over n squared minus, wait a second, z squared. And the second one is having this product as n goes from 1 to infinity of n squared minus 4z squared over n squared minus z squared, right? And yeah, so this is equals 1 minus 2 the sum actually as n goes from 1 to infinity of Riemann zeta of 2n z to the 2m. And now we don't need to carry these like two infinite products, because eventually they both are going from n equals 1 to infinity. So we can just combine that and we can write that as a single product, actually infinite product, I'd say. Okay, let me just check the recording is, yeah, it's perfectly going on. And let me just write it in a neat manner, I would say. So it's the product, and the arguments are gonna multiply to each other. So that's gonna be n squared times this argument, n squared minus 4z squared over n squared minus z squared, and times this n squared minus z squared, and that equals to 1 minus 2, the sum as n goes from 1 to infinity of Riemann zeta of 2n and z to the 2n. Okay, so basically this product is gonna be the product as n goes from 1 to infinity of n to the 4th minus 4 n squared z squared over, it's gonna be n squared minus z squared whole squared, because the similar terms are being multiplied to each other, and this is actually, yeah, okay, so this is 1 minus 2 times the sum, this thing, right? Okay, so now I'm just gonna look for this sum, and rather these two terms are gonna be like sent to here actually. And how is that gonna be happen? Let me just show you, don't worry guys. Okay, so we can just add both sides with this infinite sum, right? Actually 2 times of that, so that's gonna be 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n equals 1 minus the product as n goes from 1 to infinity of n to the 4th minus 4n squared z squared over n squared minus z squared whole squared. And now we are just going to divide both sides with 2 in order to get this infinite sum. That's it. So the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n equals 1 over 2 minus 1 over 2 times the product as n goes from 1 to infinity of n to the 4th minus 4 n squared z squared over n squared minus z squared whole squared. So here it comes the final representation of the sum of the infinite sum of Riemann zeta functions of even arguments that is being represented with an infinite product. Like, isn't this sounds crazy, guys? And that too can be like, we can just talk about the infinite sum of the Riemann zeta function only of even arguments. We can just hide this z terms when we plug z equals 1. So like literally, I think this is amazing, and I have never heard of that. I have never seen this thing in ever. So if we talk about when z equals 1, so when z equals 1 here, so it's the sum as n goes from 1 to infinity of Riemann zeta of 2n equals 1 over 2 minus 1 over 2 times the product as n goes from 1 to infinity of n to the 4th minus 4n squared, since z is 1, and it's n squared minus 1 whole squared. So the sum of Riemann zetas of even arguments equals infinite sum actually equals 1 over 2 minus 1 over 2 times the product of n to the 4th, infinite product actually, of n to the 4th minus 4n squared over n squared minus 1 whole squared. Oh my goodness, that sounds crazy. Oh my god. Like, what? Basically this is Riemann zeta of 2 plus Riemann zeta, wait a second, Riemann zeta of 2 plus Riemann zeta of 4 plus Riemann zeta of 6 plus dot 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 to infinity equals, like literally this is 1 minus 2 over 1 minus 2 product of n to the 4th minus 4n squared over n squared minus 1 whole square. Oh my goodness. Like literally. And we have not talked about the standard form of the cosine function that represent, like that is the representation of the cosine function as an infinite product. We just talked about our, like the one that I have proved anyhow. Now I think let's talk about that as well, because this is being crazy. This is literally, and I'm literally not believing on this, because like how is this how is that possible even? Oh my god. Okay, so just take a look at this scenery. Wow, that's amazing, dude. That's amazing. Okay, so we have this pi z over sine pi z as an infinite product, and we have cosine of z, the standard one. Cosine of z equals the product of 1 minus 4 z squared over 2n minus 1 whole squared pi squared. And now if I talk about cosine of pi z, so that's gonna give us 1 minus, because pi squared is z squared over pi squared, so that's gonna give us 4z squared over 2n minus 1 whole squared. And that can also be written as cosine of pi z equals 2n minus 1 whole squared minus 4z squared over 2n minus 1 whole squared. Let me just write that down a little bit here as well. So cosine of pi z can be written as the infinite product of 2n minus 1 whole squared minus 4z squared over 2n minus 1 whole squared. And now we can just multiply the one that we have evaluated earlier, the pi z over sine pi z as an infinite product. So basically that is pi z over sine pi z equals the product as n goes from 1 to infinity of n squared over n squared minus z squared. So we just have to multiply these two things, and then we can just equate that to the right hand side of our this infinite sum of cotangent function actually. Yeah, that's again crazy. So it's product of n squared over n squared minus z squared and times the product of 2n minus 1 whole squared minus 4z squared over 2n minus 1 whole squared. Yeah, and that was equal to 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n, right? And finally we are good to go with our final result here, that is the product. Well, it's not the final, we have to just I'd say we have to separate all these things, like we have to just talk about this infinite sum actually. So it's n squared times 2n minus 1 whole squared minus 4z squared. over it's n squared minus z squared and 2n minus 1 whole squared, right here. And that is being equal to 1 minus 2 times the sum as n goes from 1 to infinity of Riemann zeta of 2n z to the 2n. And now we have to just separate 1 and minus 2 that is in front of the infinite sum. Let's do that. So here we are having the sum as n goes from 1 to infinity of Riemann zeta of 2n times z to the 2n equals 1 over 2 minus 1 over 2 times the product. Let me just consider writing this here. 1 over 2 minus 1 over 2 times the product as n goes from 1 to infinity of n squared times 2n minus 1 whole square minus 4n squared z squared over, okay, yeah, and it's n squared minus z squared and times 2n minus 1 whole squared. So this is what we are having. This is quite long actually. And if we talk about the infinite sum of the Riemann zeta of even arguments, so we have to plug z equals 1. So here we would be getting rid of that z term as well as everywhere, like this is gonna be 4n squared actually, and this is gonna be n squared minus 1. That's it. So our final thing is we are having again another representation actually. So the sum as n goes from 1 to infinity of Riemann zeta of 2n comes out to be 1 over 2 minus 1 over 2 times the product as n goes from 1 to infinity of n squared 2n minus 1 whole squared minus 4n squared over n squared minus 1 and 2n minus 1 whole squared. Oh my goodness, just take a look at these things. And the one that we have got earlier was the sum as n goes from 1 to infinity of Riemann zeta of 2n 1 over 2 minus 1 over 2 times the product. That was around, what was that? Wait a second, let me just remind that. So it was n squared and yeah, I think it was n to the 4th minus 4n squared over n squared minus 1 whole squared. So yeah, this is what we were having actually. And here, like, can we say that the right hand sides of both the things are same? It means basically this product equals this product. Is that true? Because the way we did that is saying us to prove that, or maybe to say that basically the product, wait a second, so the product as n goes from 1 to infinity of n squared times 2n minus 1 whole squared minus 4n squared over n squared minus 1 times 2n minus 1 whole squared equals to this product, that is n to the 4th minus 4n squared over n squared minus 1 whole squared. Oh my goodness, is that true? Whoa, mathematics is like, oh my goodness. Guys, just take a look at these things that I have written on the boards. Is that really true, guys? Because the things that we're having, I don't want to say anything here. I just want you to say something over this. Oh. Ah. Now I cannot do anything because I'm having something trouble in just recognizing these things and just saying these things that yeah, these things are true. Well, the way we did that is not wrong, and I'm sure with okay. You know what? Maybe you think that Aman, you must have evaluated or yeah, the proved. You must have proved wrong. Like you must have wrong proved actually the infinite product of the cosine function that you said was yours. So maybe, but well, the way I did is not wrong. And I'm literally requesting you guys to just watch my videos and just tell me whether it is wrong or right. Oh, this is mind blowing. This the way I can see the things here. We did these three things. I was literally not sure. Actually, you know what? What I just thought for this video, I thought for this video that it would be done in within 9 or 10 minutes actually, because we just have to prove these two things, or maybe do one of these two things actually. But I just made myself in the flowing river and just diving into this. Oh my goodness, look at those things. Whoa, that's not cool, or maybe that's so cool, or it's not cool. Okay, guys, I think it's enough and I cannot go further in it, right? Because look, it's 2n minus 1 to the 2n minus 1 whole square, and we're having n squared, like n squared times 2n minus 1 whole square, and this can be written as n squared times n squared, right? So and minus 4n squared, yeah, it is same. Like basically what the hell we did here is that, like on the numerator where the difference is n squared is being represented like replaced with 2n minus 1 whole square, and in the denominator if we had n squared minus 1, so that would be the whole square. So this is the numerator stuff, and for the denominator actually numerator, and for the denominator 2n minus 1 whole squared actually, or maybe yeah. Oh wait a second, let me just explain it to you. I think I'm wrong here because there is no possibilities of me to be right there. Basically in numerator 2n minus 1 whole square is being replaced with n squared, and in denominator we are having 2n minus 1 whole square is being replaced with n squared minus 1. Does that make any sense? I'm pretty sure that this is wrong, but the way I did that and the thing that I am looking at, these two things are true. Oh, okay. I think it's enough, guys. I don't want to blow my mind here. I don't want to just bomb it through these things. Actually, I'm sick and I don't want to just suffer with these things as well. So for now, guys, it's fine. And again, guys, if you got to learn something from this video, just make sure to like, subscribe, and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. And again, if you got me wrong anywhere, any point, it's your responsibility to just encounter me over there that Aman, you did something wrong here and you have to admit it. Well, I'll admit it because I did wrong and I have to just admit that. I'm not a mathematician actually. I'm just a learner of mathematics and I have to do wrong things. I have to be failure before doing something. Okay, I'm not a motivator. It's fine, guys. Okay, goodbye, guys. Take care. Love you. And stay tuned for the next video, guys, because a lot of things are on the way. I'm just waiting this video to be 40 minutes because it's just 5 seconds left. Okay, 56, 57, 58, 59, and 40. Goodbye, guys.